Okay, this section is on the materials that come out of volcanoes. So we'll start with lava flows. That's the like molten rock that's going to come out of the volcano and move over the ground. Then we'll go into the pyroclastic debris that fly up out of a volcano. And then we'll talk about the gases that propel those eruptions. So lava flows. Here's a beautiful lava flow here where there's a little cars for size. This is from Hawaii, and the lava has flowed over the highway here. So a lava can either be really runny. So in this image, pretty clear that this lava flowed really easily over the highway. That's a runny lava. There'll be other lavas that will just stay inside the crater of a volcano. And that depends on the viscosity. So when you think of the word viscosity, in your head say the resistance to flow. So viscosity is resistance to flow. And that depends on the silica content. So remember, in igneous rocks, we can get partial melting and different ways to change the composition of a magma. So the silica content or the iron content or the magnesium content can dictate whether or not a lava flows really easily across the land or just stays right inside the crater of the volcano. The reason is the more silica there is, we'll talk about this a little later, more silica is going to create more of those little pyramids, those silica tetrahedra, and as more of those linked together, the lava gets really stiff and really viscous, really highly resistant to flow. Temperature also matters. So as the lava cools down, it's going to get stiffer and stiffer and stiffer, and also gas content. The gas content matters too. So we'll look at all that. So in this image, here is lava that is coming out of the volcano, and it flows very easily. This is a basaltic flow. It's mafic, not a lot of silica, and flows really easily. Here's an andesitic flow, more silica rich, and it's going to just flow a little bit out of the crater. And then the last one here is a rhyolitic, which is very felsic. Let me move my picture. Ooh, I'm moving around. And it is going to be very viscous and just dome up right inside the crater of the volcano. Because all those tetrahedra, those triangles, can't make one with my fingers, are linking together. Okay, let me move my face again. So basalt is first. La 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 la. This lava is flowing like a river out of a volcano. It's mafic, it's low silica, there's not tetrahedra linking together, low viscosity, low resistance to flow. So a basaltic flow is kind of like liquid coming out. It's fluid, it's going to flow really fast, 30 kilometers per hour. It can flow a long ways, they can flow until they cool down. So till it cools down, it's just going to flow. Several hundred kilometers. Most flows measure less than 10 kilometers because it's going to cool off in the atmosphere and eventually solidify. There are lava flows that flow really long ways and lava tubes. So here's a video from the Park Service I want you to click on in the static lecture in just the PowerPoint slides about lava tubes in Hawaii. So it's kind of a quirky little video about lava tubes, but they look like this. So we can peer down through this window into a lava tube and the lava is rushing by. You'll see that in the video. In this image, this picture here, here's a lava tube that over time has cooled, so there's no molten lava in it, and then you can walk around inside the lava tube. But imagine it just being a pipe and lava just cruising through that pipe underground. That's a lava tube. Move my face again. Whoop. So as the basaltic lava cools, it kind of gets a skin on it, and that skin then can get kind of dragged along, and you'll get these ropey lavas called pahoehoe. That's a Hawaiian term, glassy, ropey texture lava. And Yeah, so it just kind of gets rolled and dragged along and makes like a skin. The opposite to that is a So an lava is really chunky, hard bits, jagged. It's in the background here. The foreground has some more pahoehoe, but this lava is going to cool and get really thick and crack and turn into chunks. And it's called because when you walk across it, you're going. So two kinds of basaltic lava flows in Hawaii: the pahoehoe, that ropey lava, and then the is the jagged lava. Basalt can also form these really beautiful columns. So it's called columnar jointing. And when the lava flow's cooling, it contracts and makes these columns. And when you look at the cross section of them, they're beautiful little big hexagonal columns. So let me move myself again out of the way. There they are. Columnar jointing. And the base of this cliff here is you can see the columns are going to break off in pieces. Really neat. We've seen this before when we looked at the oceanic crust, pillow basalts. You can look back at igneous rocks and find the video of the lava erupting on the sea floor, and as it erupts, it cools, and then maybe it breaks, and another blob forms over here. So those are the pillow basalts, these rounded blobs. There's a good image of it there. And these are, I can't find a place for my face. These are really common on the mid-ocean ridge where the plates are pulling apart and that basaltic lava is coming up, and you get blobs forming out on the seafloor. Okay, switching gears now to an andesitic lava. So these are the ones that are more viscous because they have that higher silica content. The tetrahedra start to touch each other and it gets thicker and thicker and thicker. So they're not going to flow very far. They're going to mound up near the vent and be andesitic, like an andesite. This is a rhyolite. So rhyolites barely flow at all. They just become kind of a dome inside the crater. There's so much silica in them. Those tetrahedra are all touching each other and just make it a really stiff, viscous lava. So it rarely flows anywhere. It just kind of becomes like a plug inside the crater. We call that a lava dome.